quantum observable, I mean, an essentially self-adjoint operator. Okay, I'm not going into functional analytical details here. This is not the place, of course. So I suppose that A is defined on a dense domain here in L2. Okay, I'm not going to be very rigorous here, just to have an idea. Suppose, yes, I'm working in some Hilbert space, so suppose I take an element of this Hilbert space, which is equal to L2 here, different from 0, and then I define the expectation value of A in the state psi, as people say, I think, in quantum mechanics. I don't like the bracket notation, but that's a question of personal taste, of course. Yeah, okay. The brackets here is represent the ordinary L2 product. I think this is the standard definition, okay, of the expectation value here. And then you define the delta A by the following formula. One should be aware of that it's always relatively to a certain state, okay? Delta A squared equal to the average value of A squared in this state minus A squared in this state. I think this is the standard definition of the standard deviation, let's call it, and so on. Good. Let me also introduce the covariance. The covariance of two operators A, B in the state psi. Suppose I have a second operator having similar characteristics. This is 1/2 of the average value of AB plus BA state psi. This is a definition. Okay? It's a definition. It's here. The definition is taken by analogy with the situation in classical statistical mechanics. Okay? Good. And then you have, yes? No? No, well, I suppose that AB and BA are defined in a common domain and so on.
No, I'm not even that. I'm just trying to sort of subtract something like that.
No. No.
The product of domains?
No.
Okay, no, I'm leaving.
No, because we cancel.
We cancel.
Then we have the following result. Proposition or theorem or result. Suppose that the variances and the covariances are well defined and so on, then delta A squared psi, delta B squared psi is larger than or equal to the covariance of AB psi squared minus 1/4 of the average value, yes, this is correct, of the commutator AB squared in the psi. So this is the most general version of the uncertainty principle here. Okay? And you can notice that this number here is negative. Why is it negative? Well, just because AB, the commutator of AB, is antisymmetric, of course. It's antisymmetric. So the average value, the square should be here. So this number is pure imaginary, so when you square it, you get a minus sign, which then cancels this one here. And how do you prove it? I'm not going to prove it in detail, but the proof is quite classical. It's based on Cauchy-Schwarz inequality. First, we can very well assume that the average value of A is equal to 0, okay? You can center the stuff here. In which case, it's the same thing here to prove that, or what you get is actually that A squared psi B squared psi here is larger than or equal to, I'm just doing that to show you something here, to AB psi, and this should be squared. Yes. Okay. Doing some manipulations, actually, you show that it is sufficient to prove this. Now, in the classical proof of Heisenberg's inequality, this is the first one, the naive one does the following. Well, write that AB is equal to 1/2 of AB plus BA plus 1/2 of AB minus BA, that is 1/2 of the commutator, okay? And one puts this inside here. So this leads to, of course, what we get is then taking the moduli, this one gets 1/2 of the covariance of AB psi squared minus, where did it go? Yes, minus 1/4 of AB commutator here, squared psi. And one says that, okay, this term here is positive anyway, positive or 0, so this is going to be larger than or equal to this here. And then one takes A equal to the position variables, B equal to the momentum variables, and one gets this. In other words, by forgetting about the covariances, one does not get this relation. Observe that this here is not invariant by linear transformations. Well, okay, you can swap P and X, that's all. You can rescale the P's and the XJ's, then it won't change. But this behaves very badly under general linear transformations, and even under symplectic transformations. Whereas this one does not, because we have this. So in a phase-space perspective, the only valid or good form of the uncertainty principle is this one here. I'm not going to prove this here because of lack of time. It's not very difficult. Actually, what you do is that you rewrite this inequality, taking into account the definition of the covariance matrix here. Oh, what's sigma xx? That's just delta x squared. Sigma xp is the covariance of x and p. This is the transpose of this, and this is the variance of variance delta p squared. That's all. In the general case, it's the same thing. And by exploiting the fact that this is positive semi-definite, you show that this condition is equivalent to, let me write it here, to the relations, to these relations together with delta pj, delta xk, for j different from k, superior to 0. It's linear algebra. It's purely linear algebra. But what then becomes apparent is that we have something which is invariant by symplectic transformations. Why is it so? I claim that sigma plus I h bar over 2 j larger or equal to 0 is equivalent to st sigma s plus I h bar over 2 j positive semi-definite. And the proof is almost obvious if you remember the definition of a symplectic matrix. I can left multiply this by st and right multiply by s. This will not change this inequality because st is positive definite itself. That's one way of seeing things. But then you notice that stj, s is by definition of a symplectic matrix equal to j, hence where it is. So this proof is almost a triviality. Okay, so it's not obvious at all if you look at this, that this should be symplectically invariant. But it is, if you notice this here. Now, by doing some calculations, not very difficult calculations, you evaluate the symplectic capacity of this ellipsoid. Here, take a look at an ellipsoid associated to the inverse of the covariance matrix. Here. This is what I call the Wigner ellipsoid. Ellipsoid, V sigma minus 1 is defined by the simple conditions 1/2 of sigma